Hello, welcome everyone. So we're very happy to have Elina Robeva here today, and she will tell us about graphical models and causal discovery. And how do you like people to ask questions?
Um, yeah, they can ask as I'm going, or they can ask at the end. But anything is good. They can talk, or yeah, yeah.
Okay, well, are you going to be following the chat or
I could try to follow the chat, but if you see I miss something, maybe you can stop me. Yeah.
sounds good? Okay, so yeah, go ahead.
Okay. Thank you. So today I'll talk about two kinds of graphical models. So there's undirected graphical models and directed graphical models. And I'll start by talking about undirected graphical models. Uh, okay. So. And I'll start by an example. Suppose we have four cities, A, B, C, D, and there's maybe a big mountain in the middle, uh, and we're interested in modeling the weather patterns in these cities. Okay, and so for simplicity, we're just going to have. I hope everybody knows what a random variable is, and I'm not really going to use anything technical about this, but we're going to be talking about random variables because things are random. And today, for each city, I'm going to have a variable, let's say xa, xb, xc, xd, which that take two values, 0 or 1, and they're 0 or 1, depending on whether it is rainy in that city or not, or sunny in that city. Okay, and so the same definition for the other cities, rainy or sunny. Okay, so all of these variables, they lie in 0 to 1. And there's some question, the set 0, 1. And we're going to ask some questions like, what is the probability? And I'm going to say prob of something, some event, that, for example, it's rainy or sunny in some given city, for example. So, for example, if A was Vancouver, the probability it's rainy would be 0.7, and the probability it's sunny would be, let's say, 0.3. Maybe if B was San Francisco, then the probability that it's rainy will be 0.1 or less, I don't know. And the probability it's sunny would be 0.9, let's say. Okay, so those are some simple questions, and these questions we can answer from data, right? So in the back of our mind, this is sort of an applied kind of modeling question because we'll be observing some data, like we have historical data, and we want to say what's the probability, and how do we check? Well, we just see how many of the observations have it being rainy in Vancouver versus how many of the observations have it being sunny in Vancouver, and that's how we can decide. Okay, but we'll be interested in more complicated questions. For instance, what is the probability, the joint probability of all four taking some particular value, like xa is 0, xb is 0, xc is 1, xd is 1, for example. Okay, so that would be like one question. Or maybe maybe you've observed the weather in 3 of these cities, and you're wondering what the weather will be in the 4th one. For example, we might be asking, what is the probability that xc is 1, given that we have seen, so this is my notation here, now I'll define it vaguely here, given that I know that, I have observed a certain weather pattern in the other cities. So this straight line here can be read as given that, or conditioned on. Okay, so conditioned on us having observed that, these guys are, that these guys are like this. Okay, and so we do this modeling with undirected graphical models. Basically, these models, undirected graphical models, and these models allow us to somehow capture the relationships between these variables. Like for example, here, if we, with a graph, okay? So for example, if there's a mountain in the middle and we have these four cities, I mean, now A and B are not Vancouver and San Francisco anymore. You can imagine different cities somewhere. If we have the mountain here, then presumably the weather in A will not affect the weather in C except through B somehow, okay? Because the mountain will block all the weather patterns. Okay, and so we're going to define, so today what I'm going to do is I'm going to just define these models. I mean, this is a whole field, so it's just a little introduction into what, what things look like in this field. Plug this in. Okay, so we're going to define undirected graphical models in two ways. So there will be two definitions. Two definitions. And I'm going to sort of allude to this here in the example. So the first definition I call Markov properties. And it says properties because there's several Markov properties. That's how they're called. That's just the name. But today I'll just talk about one of them, which is the main one called the global Markov property. But the point is that if we had this graph, so I'm just going to define this all in an example, and then I'll give you the general definition afterwards. So if we had this graph, then as I was alluding to earlier, all the information, so if you wanted to see how A is related to C, well, all of the information from A that we can use for C can sort of be read off from B and D. So if you knew B and D, if you knew the weather in these two towns, then the weather in A will not be giving any extra information about the weather in C. So the way we say this in probability is we say XA, this random variable, is independent of XC given XB and XD, so or conditioned on. So this here is independent of, perhaps you all know this, I'm not exactly sure. And this is again given that or conditioned on. So I'm not going to define conditional probabilities and independence right now, but you can just think about it intuitively, what it means, and it maybe you already know. That's great. And if you don't know, it's also totally fine. Okay, so this is one. So this is a conditional independence statement. So conditional independence statements. These are the Markov properties. So they tell you if you're given a graph, then there's certain conditional independence statements that hold. And another one that holds, maybe someone can try to tell me, I don't know if it's common practice for speakers to ask. Can you come up with another conditional independence statement that holds in this graph? Similar to this one.
XB is independent of XD given XA and XC, XA or XC.
Yeah, exactly. You need both. You need both XA and XC. So this means like both things. Yeah, exactly. So, and same logic here. So B does not really influence D if you know A and C already. Okay, so we'll explain exactly how to define this. So that's one way to define the graphical model with respect to this graph. It's basically all random vectors or all probability distributions of these variables XA up to XD that satisfy this, okay? That satisfy these conditional independent statements. And the second way to define it is through something called factorization. I'll give you a slightly more formal definition in a little bit, but basically what this says is that now if we have this graph, then the probability mass function, which is basically for every possible assignment of values to XA, XB, XC, and XD. So, so these little a, b, c, and d could be 0 or 1. So there's 16 ways to do this. For all of these 16 possible options, this, we can define this probability that they happen together, this joint probability. And this factorization definition says if X actually lies in the graphical model for this graph, then this probability should be able to factor into these factors like this. So
Wait, so this is essentially looking at like the edges of the graph you have.
yeah, so it's looking at edges. In fact, you're looking at cliques. So here the edges are the cliques, but the definition is cliques. I'll give you the definition just in a second. But basically, this says that you can write this function of A, B, C, D as a product of functions that only depend on AB, BC, CD, and AD. So it's a function that factorizes, and it's definitely not true that every function can factorize like this. So it's a special kind of function, and that's the definition. So it just says this. And for undirected graphical models, these do not have a probabilistic meaning. They're just non-negative or sometimes positive functions. And it's not unique, so you can scale them. Okay, and so it turns out that what these two definitions, 1 and 2, are actually equivalent, assuming that this probability is always positive for all values A, B, C. So let me just define this a little bit more generally. So given an undirected graph, I'll just say a graph because for now, G, V, E. So V are the vertices. And sometimes we want to just assume they're the numbers from 1 to n or 1 to some number. And the edges are E. And here, because we're an undirected graph, the edges are actually unordered pairs of vertices. So ij such that I would equal to j, ij, yeah, so these are the edges. Sorry. This is a subset of all possible unordered pairs. Ij such that I not equal to j, ij in V. Okay, so unordered pairs. Sorry. Of vertices. Okay, so this is our setup. We have this graph, and then so number 1, the global Markov property. So okay, so definition. Let G be an undirected graph. And let X I for I in V be random variables. So we have one random variable for each vertex. So we just place each one in a vertex. Then X, which is basically a vector that contains all these variables, satisfies the global Markov property with respect to G. On G. If the following happens, so if for all disjoint sets, actually, no. If for all A, B vertices and C subset of vertices, which is not A or B, such that C separates A and B, A and B in G, and I'll explain what this means. X sub A is independent of x sub b conditioned on x sub c. And c here is a set of variables. Oops, sorry. This one. But x sub c means just all of the variables that lie, like x little c for little c and big C. So just like before we had like before in our example here we had this, right, B and D, right? So the set would just be B and D. And what the definition said now is that you just pick two vertices, A and B, and you want them to be separated. So let's say we pick these two. They're independent, conditioned on a set that separates them in the graph. And that means, what separates means is that every path from A to C has to pass, sorry, every path from A to B has to go through C. So here's an example. Actually, I have an example. So that I don't confuse the letters. Okay, so just some, I mean, there's a lot of different options. Okay. Let's say we have this, and so then this could be A, this could be B, and for example, these three could be C. Okay, so in this case, oh, sorry, little. Okay, so I can pick any vertex, little a in A and little b in B, and they are separated. So A, like if I picked A to be here, B to be here, they're separated by C. Okay, so here's C. All right, so this is the global Markov property. Again, basically your vector satisfies the global Markov property if for every two vertices that are separated by a third set of vertices, you have this conditional independence statement. Okay, so then that's one way to define the graphical model. And the second way, which we also already alluded to, is the factorization definition. Which says that okay, so the probability mass function, and here, what is the probability mass function? So this is the probability distribution basically for a random variables that take discrete values. All of this works for continuous variables as well. I just don't want to get into probability very much. I just wanted to talk about more the graph part of it. So, but like for every, so what is this? Is basically the probability that each variable equals something. And these little xi's could be, they vary through all the possible values that your variables can take. So for example, in our example with the weather, rainy or sunny, little xi could be 0 or 1. But in another example, they could take, 3 values or 50 values. Okay, so the probability mass function factorizes according to the graph G, which again has vertices Z and edges E. Sorry. If for all cliques C subset of V, I'll say what a clique is in a second, there exists a non-negative function psi C that depends on just the variables, or maybe I actually have a better way of writing this, x sub I, where I is in C. Oh, what did I do? I think I made this thicker somehow. So that, sorry. So that this probability mass function, I don't know why my pencil became thicker, is the product over all cliques. So C subset of V clique of psi C of xi I in C. And these psi C's are actually called clique potentials. Okay, and so okay, so just recall, maybe I'm sure you know, but C is a clique if it's fully connected. So in G, if for every A, B, and C, the edge AB is an edge. So it's a fully connected subgraph. Okay. So we have two definitions. One says that the probability is factorized, and one says that we have these conditional dependence statements. Again, if you know what conditional dependence statements are, they can be defined with respect to like this probability mass function. So it says that the probability mass function factorizes in a certain way. But in any case, there's these two definitions, and I was going to say about their equivalence, but just one more note here on the second definition is that we may assume that only maximal cliques appear in the factorization. And why is that? Well, basically, if there is what is a maximal clique? It's a maximal fully connected set. So I don't know if I have an example here. Okay, let's say this was an edge here, then you know, this here would be a maximal clique, these four vertices, but any subset of it, like this one is also a clique, but it's not maximal because you can add another vertex and it's still fully connected, still a clique. And so if you had this factorization that didn't use only maximal cliques, you can, for any clique that's not maximal, it's a subset of another clique, a bigger clique, so you can define the clique potential for the bigger clique to just multiply it also by this one. So you just group the functions together, group these psi C functions together, so you only use the maximal cliques. So anyway, this is the definition. These are the two definitions, and they sound quite different. And now I'm just going to present a result that says that they're equivalent, more or less. So here's a result. And so there's two parts. So one, 2 implies 1. So what it was 2 was the factorization definition, and it implies conditional independence. And here one has to just look up the definition of conditional independence, and it says something about how, actually it says something about how this factorizes, and you can use this factorization to prove it. And actually I'm leaving this as an exercise. It's oftentimes I usually leave it as an exercise when I teach the class, a homework problem. And then the second part, which is actually the more difficult part, it's called the Hammersley-Clifford theorem. It's the other way. So, and it's not always true, actually. So if the probability that xi equals to little xi, so if this, probability mass function is always positive, so it's positive, my weird ensign is, it's positive for all values for all little xi v, so it's positive everywhere. So every possible assignment has a positive probability of appearing. Then one implies 2. So then the conditional independence statements imply the factorization. So that's that's the other direction. So it's not always the case, but often the case. Okay, so this was like literally just a definition of what undirected graphical models are. And as you can see, they model relationship, they model conditional independence relationships between variables. Okay, so if some things depend on other things, then you can model them with these graphs. And there's a lot of questions that you might ask. For example, if you have data, can you learn the graph? Or if you know some of the variables and you know the graph, can you infer the other variables? And so on. So you can use this to model the world. Okay, so that's number one. And then undirected graphical models are always complemented by directed graphical models. So this is the second. Maybe I can pause here for a second if people have questions. Nope. Okay. Or empty. Okay. So directed graphical models are similar, but they use directed graphs. Okay. So, and the whole point is that they depict causal relationships. So that something causes something else. Okay. And here I'll give a small example. Oh, is it not normalized by 1/z? Yeah, a great question. Yeah, so this, there's a question in the chat. So this, yeah, usually there's a normalization constant. I didn't want to get into details. I mean, you can also just subsume it in one of the clique potentials, but yes, so yeah, it is usually normalized, but it's not, yeah. So yes, so usually, well, in order for this to be a probability distribution, it has, if you sum this over all possible xi's, it has to sum to 1. And so if it doesn't sum to 1, you have to normalize by the sum. 1/z is the sum. But you could also assume that z is already part of one of them. You can just subsume z into one of the clique potentials. It's just a constant. So yeah, but in general it is. So your normalization. And just one more thing here. I mean, these clique potentials, they're not unique in any way, because if you, first of all, you can scale by constant. If you scale one, you can divide the other one by that. But also, if you have two cliques that share vertices, you can multiply the clique potential. So let's say we have, in this example, maybe, if we consider these two cliques, they share these two vertices, right? So I can take the clique potential of this clique and I can multiply it by any function, positive function of these two vertices only. And I can take the clique potential of this clique and divide it by that function of these two vertices, and I will still have a valid factorization. So this factorization is really not unique here. Yeah. Okay. So the second kind of graphical models are directed graphical models, and they depict causal relationships. So and here I just want to show how the graphical structure, that all these conditional independence relationships which still hold are very different than the ones in the undirected case. So the undirected case is much simpler. So let's say we have, suppose we're interested in measuring the height of people in a family. Okay, so, and we're just going to have, two siblings, doesn't really matter. Height or some other trait. So let's say X is height. And let's say, because we're just looking at discrete variables here, we can say short, medium, and tall, for example. Or, I mean, you could just imagine any characteristic you want to measure. And, okay. So let's maybe think about the height of the two siblings. So XB and XS, so the height of the brother and the height of the sister. Do you think that they're independent given something? For example, the height of the parents.
No.
No? Okay, so they are, why not?
Oh, given the height of the parents, right.
Yes, exactly. So the brother and the sister, their heights are independent given the heights of the parents. Why? Because if you know basically the whole genome of mom and dad, then the brother will not tell you anything in addition about the sister because, yeah, does that make sense? Okay, unless like maybe they didn't allow each other to eat, like the brother ate all the food of the sister or something like this, but let's say that didn't happen. Okay. But, and you know, if we think about the undirected case, it kind of makes sense because every path from brother to sister goes either through mom or through dad, right? So there's two paths and they go through one of these. So this is sort of a separating set for brother and sister. But what about the height of the mom and the dad? Are they independent given the height of the brother and the sister? Is this true? No, that's right. And even though every path from mom to dad goes through brother or sister, it is not actually true that, you know, the heights of the two parents are most likely, so this is not true. Maybe I should use a different color. Oops. The heights of the two parents are actually just already independent. So they're just two random people that you pick and they have independent heights.
Doesn't that also mean they're independent given the height of the brother and the sister?
Oh, great question. No, it doesn't, because if you condition on the brother, if you know the height of the mom and you can condition on the two siblings, the two children, and then you actually can infer something about the height of that. Because let's say the mom is short, but the two siblings are tall. Then that tells you it's more likely that the father is tall. So it's actually not.
Okay.
Yeah.
Yeah, thank
But
you.
doesn't the arrow imply that like the mom's height would imply the sister's height, but the sister's height wouldn't imply the mom's height? So how do you like reverse it? What's the point of the arrows in that case?
Sorry, 1 second. Can you ask your question again? My iPad stopped working for a second.
So like there was an arrow pointing from the mom to the sister and an arrow pointing from the dad to the sister, which I assume means that one affects the other, but the other doesn't affect the first. So how could you like construct a path backwards? Because the sister wouldn't give you any information about the mother, right?
Yeah, the sister, so if you condition on, well, it doesn't, the information doesn't necessarily flow backwards. Sorry, my thing stopped. I mean, in this particular example, you can just think about it intuitively that if you know, basically, if you know the height of the sister, and let's say the dad is tall, as I said, and the sister is short, then the mom is probably short, like she's more likely to be short. So it does give you information. It's because the sister's height is caused by both of them. And so you can, and it's positively correlated with both of them in some sense. So you can, even though the arrow is pointing the other way, I think it still gives you information.
So like if there were three nodes pointing to the sister and you only had one node you only had the information of one node pointing to the sister, then you couldn't say anything about both of the other nodes. You would need, like, if for n nodes pointing to another node, you would need n minus 1.
Let's see, like this.
Yeah, so you would need all but one to determine the last one.
To determine, oh, this one? Okay, so you mean these to determine this one? And
Yeah, like given the sister.
yeah. So, okay, you're not determining the height of the mom completely. You're just saying that these variables are not, they're dependent. So that means that there's some shared information between them. They're not just totally independent.
Okay.
So you're not actually determining the whole thing, but you can say something. And yeah, so here any pair of nodes would be dependent given the sister. So yeah, they're originally independent, but once you make them point to something, they become dependent given that thing. Yeah, I don't know.
Thank you.
Okay, because you're asking all these questions, I wasn't going to give the definition here, but I will because I think this will be interesting. Okay, so let me get to the details. So let G be a directed, the notation is the same, VE, be a directed graph. And here V is the vertices again, say 1 through n, and E are now directed edges. So sorry, it's a subset of this, of ordered pairs, IJ, such that I and J are in V and they're different. Okay, sometimes we denote it by I arrow J. Okay, so for example, we had this graph just now. Okay, and again, we're going to have random variables. So xi for I and V are random variables. And how do we define the graphical model with respect to the given graph? Again, there's two definitions, exactly the same kinds as before. So one is the global Markov property. Maybe I call it directed global Markov property. And this is a bit of a technical definition that people usually omit when they're giving talks, but I think you'll find this interesting. So X satisfies the directed global Markov property on G. Paste. Okay. On the graph G. If for all A and B vertices and C subset of vertices, just like before, we would be wondering whether A and B are separated by C, but it's a bit of a different definition. So such that A and B are something called D-separated by C. We have that XA independent of XB given XC. Okay, and so let me try to explain what D-separated is. So there is some notion of separation, but as we saw in the example just now, it's a little bit more complicated because the arrows actually matter. Okay, so let me try to define what D-separated is. Okay. So first, a path between two vertices. We just mean any kind of sequence of edges, and they could be, it doesn't really matter what way the arrows are pointing. So a path between A and B is just anything of this sort. And along this path, there could be different kinds of, two kinds of vertices. So, and I'll just call these V1 up through, let's say this is V0 up through VK, I don't know, and this is VK. Okay, so I'm gonna label these vertices, and there are two kinds of vertices. One is a non-collider. Okay, maybe I'll say what a collider is. So collider is when two arrows collide at this vertex. Okay, so there's two colliders on this path. Okay, so it's basically vertices VI that have both arrows pointing towards them. And a non-collider is any of the other three options, right? So a non-collider could be if the path is going this way, or if it's going this way, or if it's going, both of them are going out. Okay, so there's these two kinds of vertices on a path. And now, what is deseparation? Okay, so now A and B are deseparated by C. If every path between A and B in the graph, A and B, either there's two cases. So one, either the path has a collider not in C or any of the ancestors of C. What are the ancestors of C? Well, it's what you think it is. So if this was C, then maybe I use a different color. So if this was C here, the ancestors of C are any vertices that have a directed path to C. So yeah, just ancestors, like the way you think about it. See, these are all ancestors. Okay, so the two vertices are deseparated if every path between them either has a collider that's not in this set or has a non-collider that is in the set C. Okay, so let's just look at this graph again. Maybe easiest is just to look at 1 and 2. Okay, so remember we did say that 1 is one and 2 according to this definition, right? So the definition says, remember, I'm just going to scroll back up to it for a little bit. So for any two A and B that are deseparated by C, we have this independent statement. Okay, and if you remember, we did say in this graph that x1 and x2 are independent given, so x1 independent, x2 given x3 and x4. So presumably 1 and 2 are deseparated by 3 and 4. And let's see why that's the case. So there's two paths. Sorry, I'm saying something wrong, completely wrong. Ignore this. It was the other way. X3 is independent of x4 given x1 and x2. Sorry, the other one was totally wrong. Okay, so the brother and the sister were independent given the parents. And let's look at the paths from 3 to 4, right? So this path and this path. One on this path, one is a non-collider, right? It just goes, it's pointing out of 1. And 1 is indeed in this set 1, 2. So here what we're saying is that the set 1, 2, 1, 2 deseparates 3 and 4. Okay. And also the path, this one, 2 is a non-collider and it is in 1, 2. So basically condition 2 is satisfied for all the paths. Okay, there could be a more complicated graph where, you know, there's a path that this holds for it and a path that this holds for it. Okay, maybe I can, yeah, like for example, if we had also another vertex 5 here, then we would have still the same d-separation because this path that goes through 5 has a collider and it is not in C. Okay. So this also holds in this graph. And then here's another example. X1 independent of X2 given nothing, right? So given basically empty set. So that was the other conditional independent statement that we found, right? The mom and the dad are just independent given nothing. And indeed, empty set d-separates 1 and 2. And let's check that. Okay, so if we, okay, I added 5 and now there's more paths, but if we just look at this path, for example, 4 is a collider and it is not in the empty set. 3 is a collider and is also not in the empty set. And if you go through 5, 5 is a collider and it's not in the empty set. So it's all satisfied. Okay, and I invite you to just look at some, you know, your favorite graphs, maybe on 4 or 5 nodes, and try to find all the d-separation statements. Okay, I just realized that I forgot to mention something really important, which we'll need for the other definition. Okay, sorry. Okay, so here in the definition, I forgot to mention that the graphs that we're looking at are actually always going to be acyclic, okay? So, okay, so I'm going to add this here. We need it for the next definition. We're going to look at acyclic graphs. For causal purposes, we don't want things to have feedback loops. That is possible in the real world, but it has the notion of time as well. So maybe we can model these with time-dependent causal models. And if there are cycles, if there's no time, if we just have like a snapshot of the reality, we sort of assume that there's no cycles. And just a cycle, so a cyclic means no directed cycles. Directed cycle is kind of like this. Okay, so this is not allowed. So, and a directed acyclic graph is oftentimes abbreviated as DAG. Okay, so DAGs are like the object of interest. Okay, so, and let me just say the second way to define this directed graphical model, which is through factorization definition. Okay, so let G be a DAG. And directed acyclic graph. And again, assume that the vertices are the numbers from 1 through n. And now what I'm going to say is, without loss of generality, assume we have arranged V so that there's no edges I to j if I is bigger than j. So this is called a topological ordering in this literature. So what does this mean? Just like any of the graphs I have given you, I've already arranged them in topological ordering. So the edges go from small to large. They don't go, like I don't have an edge from 3 to 2 or from 3 to 1. And I'm going to leave it as an exercise to you. Perhaps it's not so hard to see, to show that if your graph is acyclic, a DAG, then you can always find such an arrangement. And there's more than one such an arrangement sometimes. But you can always find an arrangement that is a topological ordering of the numbers from 1 through n. So you want your numbers to be ordered in increasing order, so the edges go from smaller to larger. Okay, in that case, oops. Okay, so then so this probability mass function called PMF prob xi equals xi factorizes according to this graph G if for all possible assignments of values to the vertices, we have that the probability that xi equals to little xi, I and v, is the product, I from 1 to n. And now what we're going to do is, so here the product is important that it starts from I from 1 to n. So we're starting from the top vertex and we're going down, and it factorizes as probability that xi equals to its assignment little xi given all of its, so I'm gonna move this here, given xj equals to little xj for j a parent of I. What is a parent? So this means that j points directly to I, so that's an edge. Parents are just the direct edges pointing to the vertex. So let me show an example. So let's say we have this graph again, 1, 2, 3, 4. And now here, this probability of x1 is little x1 up through x4 is little x4 equals 2. And according to this definition, I'm going to start from x1. So it's the probability of x1 equals to little x1. There's no parents here. Nothing is pointing to 1. So it's just probability x1 is x1. Probability of x2 is x2. Also, x2 has no parents either. Probability of x3 is x3. And now there's 2 parents, right? x1 and x2. And finally, x4, given x, the parents of 4 are also 1 and 2. So it factorizes like this. So this is the definition. And again, not every function can be written like this. And here note that these are actually have probabilistic meanings. Okay, I don't know what this means. Rishi, is it okay if I answer this maybe afterwards? Because I wanted to finish the talk. Okay, and so just to mention the result is that I started with 2, but 1 and 2 are actually equivalent. These two definitions, the factorization and the global Markov property, are equivalent in this case, and there's no requirement on a positivity requirement on the probability distribution. And I don't know if it's okay if I say a little bit, just like another 2 minutes of something really interesting to me, or?
Yeah, go ahead.
Okay, thank you. Sorry about being so late. Okay, so now we defined directed graphical models and undirected graphical models. And let's say we're interested in learning a directed graph from data. So how would this go? Well, you observe, so let's say you ask 1,000 people about some behavioral things like, do they exercise, do they smoke, and what they eat. They have several variables that mean these things, and what disease, like if they have this disease or if they have that disease, if they this symptom and that symptom. And you're trying to learn a graph, a directed graph, to tell you what causes what. You want to be able to say, exercise causes you not to be sick, and stuff like that. Okay, so how would you do this? Well, when you ask these 1,000 people, you can approximate this probability distribution, right? You can just say, okay, well, out of the 1,000, 40 of them had the exact assignment of, did not exercise and did not eat healthy and didn't have this disease and did have this disease. So that would be like 40 over 1,000 would be your estimate of this probability. And so basically you can estimate all these probabilities from data, from these observations. Obviously, if you had more observations, your estimate will be better, closer to the truth. So let's say you have estimated these probabilities and you want to find the graph. Okay, how would you find the graph? Okay, so this is what the field of causal discovery is all about. And it's a whole very, very big field of research. But let me just tell you one thing, okay? So you may have heard this phrase, correlation does not imply causation. And what does this really mean? So let's say I'm trying to figure out whether one causes two or two causes one. Well, it turns out that from observations alone, you're not able to learn which one it is. So these are actually equivalent. They're called Markov equivalent. Okay, and if you are allowed to do something called an intervention, where you, like, for example, when they were testing the COVID vaccine to see if it worked, they had a randomized control trial where they, half of the people were given the vaccine and half of them were given a placebo, so no vaccine, and they wanted to see if there was a difference between the outcome, like whether or not they got COVID and how bad it was. So if you can do this, then you can definitely because if you can intervene on one and there's changes in two, then yes, this is the graph. But if this was the graph and you intervene on one, two wouldn't change. So you would be able to differentiate the two graphs. But in reality, sometimes you can't do this. Like you can't, force a pregnant woman to become pregnant, to become sick with COVID to see what happens, right? So you just can't. Sometimes it's not ethical or not possible. And so in these cases, we sometimes just have to settle for equivalent graphs. And I just wanted to tell you when two graphs are equivalent and what this really means. So Markov equivalent, I promise it's not very long. These are called Markov equivalent graphs. And so if G was a graph, let's say it's a DAG, as right, it's a click graph, the MG would be all distributions, probability distributions, that satisfy, one or two. That satisfy our definition. So either one or two, it doesn't really matter, the factorization for the graph G. Sorry, so it's important on G. Okay, so this is called our model. This is actually the model consists of all distributions that satisfy this, and two graphs on the same G, VE1 and H on the same set of vertices, but maybe different edges, are Markov equivalent if they have the same models. If MG is MH. So what does this mean? Well, as I said, when we have observations, we're going to observe a distribution, like, these probabilities in one of these models. And if the models are the same, we can definitely not tell which graph it is because they each yield the same sets of distributions. So we've observed a member of this set, and it's not clear if it's for the graph G or H. And there's just a really nice theorem, and that's sort of the end of my talk. Oops, theorem by Verma and Pearl that says when two graphs are Markov equivalent. So G1, I don't know why the G1 and G2. Let's say G and H. And H are Markov equivalent if and only if they have the same skeleton. So there's two conditions. They have the same undirected skeleton. So if you remove the directions, it's the same. And they have the same sets of unshielded colliders. What is that? So if in the graph we have a situation like this, where in both graphs you have the vertices I, J, K have these edges, and there's no edge between I and K. So there's no shield. This is unshielded. Then that means this condition is satisfied. So for every triple that have this here collider and no edge here, it has to be the same in the other graph. And sometimes a funny story, this is called an immorality because there's two parents, I and K, that are not married and they have a child. It's maybe not funny for you, but I guess funny for my generation. Okay, and so maybe I'll leave you with two examples to try to figure out which graphs are Markov equivalent to this one and to another one. To this one and to this one. Okay, thanks.
Good. Thank you. So are there any other questions at the moment?
Do you work in the field of causal discovery and undirected and directed graphs? Do you work with infinitely sized graphs?
I have not worked with infinite graphs. So you have infinitely many variables?
Yeah.
Yeah, that's interesting. No, I mean, I don't have any work on this, and I don't really know of it, but maybe it exists. It's a very, very big field. Do you have an example in mind? Like what?
I have no idea. I was just hoping to hear from you, maybe some more like some interesting applications of this as well.
Yeah, I mean, causal discovery is, I mean, in science, we really want to learn what causes what, right? So it's, a lot of questions are still open. One of the things that I've been vaguely involved in, I mostly just do the math, but for example, gene regulatory networks, how genes affect other genes. So the way we currently measure cells is by each cell has the same DNA, but it expresses different genes. Depending on the type of cell, it expresses different genes. So, and we measure them by RNA sequencing. And so for each cell, we get a vector in R20,000 of numbers. And the problem is that when you measure the expression of a cell, you kill it. So you actually don't know how you start from an embryo and it changes into a fully grown organism that has skin cells and eye cells and whatever, everything. And they believe that this is done, there's a causal mechanism that if one gene turns on, like its value increases, then it increases other genes or like turns off other genes. And it's an open question to still learn how it all works and how we develop.
Okay, thank you. That's interesting.
Sorry, I just wanted to ask, are those necessarily acyclic graphs? Like, is it possible that
Yeah, so you can do cyclic graphs, and I have worked on this as well. Oh, my thing is off again. Basically, okay. You can define the factorization, you can define the Markov property. Again, the same way. Equivalence between graphs in the cyclic case is really, really difficult to define. There's like 8 conditions and they're very involved. We have a paper on learning a cyclic graph in the setting, and it's just, there's a lot of detail. So cyclic graphs are very complicated to deal with, and that's one reason people avoid them. Another reason is that in causality, sometimes it doesn't make sense because you want to be able to define these interventions. Yeah, it's a whole theory that doesn't quite go through for cyclic graphs. But what you could do is you can include time. So you can say, I have a random variable at each time point, and this way it's possible that they affect each other. But basically you have a lot of variables because they're all in one, like for each time point, I have one random variable. So then it's a big graph. Yeah, and then you can have cycles.
All right, thank you.
If not, then thank you, and let's conclude this part of the class.
Thanks.
Thank you for giving the talk.
Thanks. I'm so sorry for the late.